Welcome to lesson 11.4. Before we get started on the central limit theorem, let's review what we learned on 11.3, which went over the normal distribution. Number one says the weights of 225 high school baseball players are normally distributed with a mean of 175 pounds and a standard deviation of 14 pounds. Approximately how many players weigh less than 161, and what percent of the players weigh between 147 and 203 pounds inclusive? All right, so let's first take a look at part A here. Now, with my calculator, and while I'm here, let me go over to our digital classroom. You can go down to either daily, weekly links and select Desmos pre-programmed graphs, or you could open up this document here. And in between number 3 and 4 on the left, you will see the calculator listed in a different color blue there. Now, what I will do now is I'm going to come over here and click on, here's our calculator sheet. If I go all the way down to the bottom, there's AP statistics. And when you click that, it should open up this chart. And so for the normal distribution, one thing we've done is to simplify things. I have it plugged in here, and we could find out all of our information we need by saying, okay, our mean here is 175. The mean, that's the symbol mu, if you remember, 175 pounds. And so I'll put that in as my mean, 175. And the standard deviation, sigma here, is 14 pounds. So we put that in, 14 right here. At that stage, I'm going to click this little plus to zoom fit. It'll show me, here's my chart, and this over here is the cumulative probability, or the CDF, represented on the side. If we're wanting to know how many players weigh less than 161, that means the maximum weight is 161 pounds. So we want to know all the values that are 161 or less. So basically everything from 160, let me scoot in a little bit. That would be 161. Everything from this area over. Okay, so the way to do that is just right over here, you put 161, and it would show you that's the area, which happens to be 15.8%, or actually I would say 15.9. Let's just say that's approximately, this will be approximately 15.9% of players weigh less than 161 pounds. Now, oh, that's supposed to be a B right there. Okay, so you're looking, and this number does not show. Well, that's 15. That looks like the right answer there, except it's not. This is not a percentage. It says here we have 225 players. So really what that means is I need to take 225 and multiply by that 15.9%. Whoops, 15.9%, which is the same thing as 225 times 0.159, which means approximately 36 players will weigh 161 or less. So that would be our answer to part A there. Now on part B, by the way, we learned a formula using Z values if you want to go back to the standard normal. And I don't know if you remember, but we said the Z, you would take any of your values, which in this case, or you would take your particular value you're trying out, which in this particular case is 161. The formula, it just had a little X there for any random value minus, let me just write out the formula, divided by sigma. And so this is, if you wanted to use this, you would have had 161 minus the mean of 175 divided by the standard deviation of 14, and that would have gotten us -1. And so what we could have done is on the standard normal, that means it's a normal distribution with a mean of 0 and a standard deviation of 1. You would look at the Z value of being left 1. So I'll show you, this would give us the same exact value. If I change this to a 0 and this to a 1, and I wanted to, let me go here, look at the values from -1, you see it's the same number. So that also would have worked. All right, let's take a look now at part B. It says, so going back to this 225 with a standard deviation of 14, and we had here 161. That's what we had last time. What did I do here wrong? Let me pause this just for a moment to fix what I've got wrong here. I put in the number of players. It's 175. There, let me correct this to 175. Okay, there we go. A mean of 175 and a standard deviation of 14. There we go. We're back on track. All right, part B, it says what percent of the players weigh between 147 and 203? So I put in 147 and 203. And we want to know how many players weigh in between these weights. So we're looking at the area in between. Here would be 147. If you zoom in, you'll see that that is 147 there. Zoom in a little bit. Yep, 147. And this weight over here, that would be 203. So what percentage of players? Well, it's this area under the curve in this area, which is represented by 95.4%. So 95.4 is approximately 95%. That would be the value there. Okay, again, if you wanted to use the Z numbers, what you would do is your Z for your left bound, let's call it the Z score, I'll just do a Z with an L here for left, would equal the 147 minus the 175 divided by 14. And the Z-score value for the right side, so we'll do ZR like that, would equal the 203 minus 175 divided by 14. And this is if you wanted to use the normal with a mean of 0 and a standard deviation of 1. That means the standard normal. If you want to use this distribution, you could do so, and you would use these Z-score values. So I'm not even sure what those Z-score values are, but I'll type them in as we go here. That's a 0. This is a 1. And what I should have here is 147 minus 175. And all of this would need to be divided by 14. And on the other side, I take almost the same numbers. This time I take, the only thing different is I changed the numerator of the 147 to a 203. And you see you get the same number that way as well. And so this one, what it does is it puts the normal distribution back at the origin. And so you're seeing it standardized or made to be the standard normal. So that's why we call it standardized to a mean of 0 and a standard deviation of 1. So either way, that's how you can get your answers there. Now let's take a look at number 2. It says the weights of 500 US pennies are normally distributed with a mean of 3.1 grams and a standard deviation of 0.14 of a gram, 14 hundredths of a gram. Find each probability. Okay, so this one, just to be simple, I could just type in a 500 here. No, I'm sorry. We have 500 pennies, but it's 300 or 3.1 grams with a standard deviation 0.14 grams. I'm going to remove these values for a moment. And I'm going to zoom fit this. All right, so here is our curve. Notice the area in the curve always equals 1. This is our PDF, or excuse me, CDF. The dark line right here, this solid red line is called the PDF. This dotted line is what we call the CDF, the cumulative distribution function or cumulative probability. Okay, so anyways, we want to know what's the probability that the penny weighs less than 3 grams. So that means the maximum would be 3. So we're looking at 3 or less. We're looking at this area, so I need to put it in as a maximum. That would give me the probability of having the penny weigh less than 3 grams, which is 23.7%. So at this stage, I can eliminate this because we know it's 23.7%. The penny weighing more than 3.3. So now we want to say it weighs more than 3.3. So somewhere over here. So to weigh more than 3.3, I would not put it as the maximum. I put it as the minimum. This is 3.3 or greater. The probability is, it looks like 7.7%. And at this stage, we get the answer. And let's just try to see if weighs between 3.2 or 3.4. So something in between 3.2 and 3.4. 3.2 and 3.4. When I look at this area, I find that it's 22.1% chance. 22.1%. And so the answer would be C. So for lesson 11.4, we're going to take a look at the central limit theorem. And what this is going to do, it's very, very powerful. What it's going to do is it's going to take distributions that aren't necessarily normal in makeup, but yet as long as we have enough samples, we can view it as a normal distribution. So let me say it this way: as the number of samples increases indefinitely, you can begin to use whatever, regardless of the distribution, you can begin to use central limit theorem to solve it. And so the central limit theorem is going to basically treat it as a normal distribution, if you will. Okay, and so that's what we're going to look at today. So you might hear me say often like sampling, distribution, or things like that. So let me start off with some formulas first. And it says, so starting off, as the sampling size increases. So as we get more and more cases, we wouldn't do this if you only had 10 cases of something or 30 cases, as it increases indefinitely. So as we start getting many and many and many samples, the shape of the distribution of the sample means and the standard deviation will approach a normal distribution. So as sample size increases, it'll become more and more normalized. Secondly, the distribution will have a mean and a standard deviation. Now, I want you to notice what's going to happen. The standard deviation, when you change from the whatever distribution it was into the central limit theorem, the standard deviation, symbolized here as you learn sigma x bar or sample mean here, is going to be whatever the original standard deviation was divided by the square root of the samples. That's going to be our formula there. So the mean will stay the same. The z value, this is very similar to the formula we saw earlier in the bell ringer, will be the x bar, which means the sample mean minus the original mean, or perceived mean, if you will, divided by the new standard deviation, or what you'll learn is could be called the standard error. Okay, so with that, we have a few formulas here. It says executives of an entertainment company determined that a first-year movie revenues averages $2.1 million. They assume the variable is normally distributed, so it's assumption, with a standard deviation of 0.8 million. If a random sample of 16 movies is selected, find the probability that the mean revenue of the sample is more than 2.5 million. So kind of giving us a picture here, we're assuming that the mean is 2.1 million. I'm going to refresh this just to get rid of some stuff. And let me go back over here. So looking at the normal distribution here, we're assuming that $2.1 million is our mean. And we'd assume it has a standard deviation of 0.8 million. 0.8 million. So here's our PDF, or probability distribution function. And it says if a random sample of 16 movies is selected, find the probability that the mean of the revenue sample is more than 2.5 million. And so a lot of people are going to say, okay, so to be more than 2.5, let's just put that right here. And let's say that might be the answer. Now we have a problem. When you look at this diagram here, it doesn't seem to match the probability over here. Okay, so what gives? Well, we're looking at a few different things in this problem. First, we are going to say the mean is 2.1 million. And this is in money. And the original standard deviation was, just like we said, 0.8 million. Okay, but here's where things get different. What we're going to do here in this problem is we're going to say, all right, we have 16 samples. And of that samples, we want to say the sample mean, that's this symbol here, the sample mean is 2.5 million. All right, so what are the formulas we just saw on the previous pages? Well, the first just told us that we could find the standard deviation for a set of samples using this formula here. So that's what I'm going to find now, is I'm going to come over here and say, all right, the sample standard deviation, or the standard error, would be the original standard deviation divided by the square root of n, which means, and so again, this is the formula I'm using right here, which means I would have 0.8 divided by the square root of 16, which the square root of 16 is 4. So 0.8 divided by 4 is going to be 0.2. Okay, so there's one value we're going to need. Secondly, what we learned on the next slide is that we can get the z value using this formula here. And so we'll say the z value, it's going to equal x bar, the sample mean, minus the perceived mean or the known mean of the distribution, divided by the standard deviation of that sample, which means I would have x bar is 2.5 million minus the mean, which is 2.1, all that divided by the standard error, 0.2. Let me change this to black so you can see where I'm getting this, 0.2. Okay, so what is this value going to give us? Well, 2.5 minus 2.1 is 0.4. When you divide that by 0.2, you get 2. So that's the z value. So what that means is if I go here, now that was my curve that I said that's not looking right. What I'm going to do is just for a second here, I'm going to turn this off. Go to the central limit theorem, and I'm going to say, okay, the mean of the population or the mean of the whole was 2.1. My standard deviation of the whole was 0.8. The number of samples is 16. The mean of the sample was 2.5. All right, and I am going to now come over here. And so this is the standard deviation of the sample, which is at 0.2, the same thing we got. And so the z values, here it is, the first one for the central limit theorem. And when I come down here, what we're going to use is the normal distribution. So it's 0, 1 is the normal distribution. And we want to find what's the probability of it being greater than this line 2 here. And so if I put a 2, this picture, you can start to see matches this picture very well. And so the odds would be about 2.27 or 2.28%. This right there would be 2.28%. That's the probability that the mean is more than 2.5 million. So on this, I want to make sure you're aware that this, on the central limit theorem, it standardizes this normal curve. So it puts the mean at 0, and this value right there is 2. That's the z value of 2. So there would be the z value of 1, and so on. That would be 1, 2, and we're looking at 2. And so it would be 2.28%. All right, with that, I'm going to let you try your first. So again, what I want you to do, so you're not confused, because I know I started with a normal distribution. We're not going to use a normal distribution. We're going to use a central limit theorem. So I want you to use a central limit theorem and plug in the values to see if you can solve for the probability of the mean number of boats being less than 28. Pause the video if you need more time. Example 2. Scuba diving. A diving tank manufacturer finds that its smallest tank averages 35 minutes of oxygen. Assume that the distribution is normal with a standard deviation of 2.5 minutes. If a random sample of 25 tanks is selected, find the probability that the mean of the duration of oxygen is between 34 and 36 minutes. Okay, so again, we're going to use the central limit theorem here because we're dealing with a certain number of random samples of the whole. So what we know is on the population, the mean of the population is 35 minutes. And the standard deviation of the population, or the whole, if you will, is 2.5 minutes. Now, we are going to look at a random sample of 25 tanks. So that's our N. So N is 25 tanks. And we want to know the probability that the duration of oxygen is between 34 and 36 minutes. So we want to know what's the probability that X bar is somewhere between 34 and 36. That's what we're really trying to solve for here, is this probability. Okay, so let's start here. We're gonna have two Z values, as you can see here. I'll use my calculator to show you this. We have a mean of 35 with a standard deviation of 2.5. The number of samples we're looking at was 25. And I'm gonna leave off the mean here for a second. And so I'm gonna zoom in here. And so here's our normal distribution. But you're looking at it from 0, not from the probability of 34 to 36. So if you want to see it that way, what you'd have to do is go back up here, the normal distribution, and say, okay, our mean was 35 with a standard deviation of 2.5. And from here, we'd say, all right, what's the probability of it being between 34 and 36 minutes? Now, once again, you're looking at my curves and they're not matching, which means this must not be correct here. So I'm going to take this off again. I just wanted to show you that. All right, so we're back over here, and let me zoom in on this one. And so our x-axis is just not going to belong with this one. So how do I get my values? Well, if you remember the last problem, what we did is we said, okay, let's talk about the standard error, or the standard deviation of the population, if you will. That was calculated by taking our original standard deviation, which was 2.5, and dividing it by the square root of the number of samples, which is the square root of 25. So when I simplify this, the square root of 25 is 5, and 5 goes into 2.5 times 0.5 times. So that would be called the standard error. And so now, if I want to find my z value, and I'm going to have to find two z values. You might have saw my calculator for a moment. Let me leave that off. I'm going to do, we'll say z equals, what you do is you take your x bar. So I'm going to look at two different values. I'm going to look at 34 first. 34 minus the mean of 35 divided by the standard error, which is 0.5. So 34 minus 35 is -1. And when you divide that by 0.5, you get -2. You can type that in the calculator if you don't believe me, but that's the algebra there. But we don't have just one z value. We're actually going to have two. So I'm going to call that z1, and here it will be z2. So z2 is going to equal the value 36 minus 35 divided by 0.5. Well, this calculation is nearly the same. 36 minus 35 is +1 now, not negative, but positive. And so when you divide by a half, we're going to get the value +2. And so ultimately, if you want to look at this as a normal distribution, a standard normal, this would be 0. And what we're looking at is we want to know what's the probability of the area being between the z value 2 and -2. That's truthfully what we're looking. If this is the z values, that's where we're looking for this to get the probability. So I'm going to say from -2 to +2. The probability of having, when we draw 25 tanks, the mean of those tanks being somewhere between 34 and 36%, or 34 and 36 minutes of oxygen, is about 95.4%. I guess I rounded to 2 decimals before. I'll do the same here. This is the probability of this, probability that the amount of oxygen in terms of minutes, the mean of this sample is between 34 and 36, is approximately, that's how you would write that, 95.45%, which is a really good shot. That's a really good chance of having that mean there. So now I'll let you try one. Stop the video if you need more time. And you might have noticed, but you do not need to go normal distribution. You can use the central limit theorem with your values to solve here. When I typed in mine, let me see where I got the mean of the sample. What I would need to do for the calculator is to first put a 34, and I would have got that -2 value, which went there. And then you would do it again. Well, what about at 36? And got +2. I never completed that in the calculator. So that's how you could have got the -2 and +2, is just by changing the mean of the sample to those boundary values of 34 and 36. All right, your turn. Example 3, entertainment. A recent study reports that a high school age student or high school age students use their computer or watch the television for 5.5 hours per day. Goodness gracious, that's a lot of hours. So the mean technology use, if you will, for a day, and this would be pre-cell phones. I mean, goodness gracious, what is the number now? Is 5.5 hours per day. The variable is normally distributed with a standard deviation of 1.1 hours. Find the probability that a randomly selected high school student will use the computer or watch television for more than 6 hours per day. All right, so here we are, and we're trying to find the probability, and here's how you would like to write this: the probability that a student would watch the television for more than 6 hours per day. So that's how you would write that probability, just like that. So that's the probability of more than 6 hours. So let's go through solving some values here. Now notice they do not give us any standard sample other than to say a randomly selected high school student. So I'm going to treat my n here as 1. So let's first start off with finding the standard error here. So the standard error can be found. If you remember, you take the original standard deviation, 1.1 hours, and you divide by the square root of the sample size, which is the square root of 1. So we will have here 1.1. That is our standard error. So now let's find our z number, our z-score, if you will. And so the z value is going to equal, you take your sample mean, which in this case we're going to say is 6, minus the original sample mean of 5.5, and you divide that by your standard error here, 1.1. And so I have 6 minus 0.55, which is 0.5 divided by 1.1, and I don't know that number off the top of my head. So let's see what we get here. 6 minus 5.5, all of this divided by 1.1 is approximately 0.45 repeating. Not approximately, that's exactly what it equals, 4.5 repeating. So what does that mean? If I went to a normal distribution, this would be my z value, and I would be looking for the values greater than that. So that would be the minimum. All right, so here we go. The mean of the population was 5.5 with a standard deviation of 1.1 hours. We're looking at only one sample, and the mean of that sample is 6 hours. And so here's what we got: the standard deviation of the sample, or the standard error, if you will, with a 0.4545 repeating. Oops, that's not where it shows it to us. There's where it shows it to us. There's the z value. So when I come to my distribution here, I'm going to be looking for, I want the area all from 0.45 repeating, which is somewhere in here, over. So I put that as the minimum, 0.45454545 repeating, and that's enough to get where my decimal is not changing anymore. And you can see that this is 32.47%. So the odds of this happening, the probability that randomly selected student watches more than 6 hours is approximately 32.47%. And that's using the central limit theorem. Now let's take a look at part B. Part B has basically the same information, except now I have a sample size. So now I'm going to say, what if we said there's a sample of 20? So again, my mean was 5.5 hours. That hasn't changed. My standard deviation is 1.1 hours. But now we're going to throw in that we have n as 20. And we want to know the probability again. What's the probability that the mean of the sample is greater than or equal or greater than 6 hours? That's what we're searching for again. So to find the same two values here, to find our standard error, what we're going to do is take the original standard deviation, 1.1 hours, and divide that by the square root of the number of samples, which is 20. Again, I don't know, square root of 20 is not a great number, so I'm going to type that in over here. We'll see what the value is. These remain the same. Now I'm going to say my sample is 20. And so what we get here is 24, or not 24. I'm going to say is approximately, let me go black so I can see that it's different here. That is approximately 24.6, 0.246. Maybe I better put the 0 in front. 0.246. There we go. And so now when I want to calculate here my z value, I take again that same sample mean of 6. I subtract the population mean of 5.5, and I'm going to divide it by the standard error, which in this case happens to be 0.246. And when I do that right here, that's what the value, that's what's happening here. The mean of the sample minus the mean of the population divided by the standard error of that sample, we get this number here. Approximately 2.03. So that right there is my z-score value. So now if I look at the normal distribution, I want to know the values where that from greater than that value. So I'm going to come over here and say 2.03. What's the probability that out of these 20 students that the mean is greater than 6 hours being watched? It's only 2%. You can see there. That is not a very many at all. The probability that the mean would be greater than 6 hours if you had a sample of 20 students is only 2.12%. That's the probability for that sample mean there. So that's using the central limit theorem. Just saying, as any type of distribution has samples that are increasing, you can more and more use the normal distribution to solve for the probabilities here. This part for the guided practice, the example 3 guided practice. I want you to work through this problem and see what you come up with. Example 4, approximation rule for binomial distribution. So now we're getting away from original normal and we're going to look at binomial, but we'll use the central limit theorem. It says this: a normal distribution can be used to approximate a binomial distribution whenever n, which is the samples, times the probability of a good result, is greater than or equal to 5, and also n, which is the number of samples, times the probability of failure is greater than or equal to 5. So it gives you an example here. If the probability is 0.4 and we have 5 samples, if you multiply those, you get 2. Since 2 is less than 5, you could not use the normal distribution to approximate this binomial distribution. Now, whenever we approximate using the central limit theorem or a normal approximation of the binomial, we're going to first find the mean and standard deviation. We will write out our probability. That's the P of X that you saw me write earlier this lesson. And we're going to be using what's called a continuity correction factor, which is up ahead in the notes just a little bit. That we'll find the corresponding z values, and then we will solve our solution. Okay, so here's the first problem we're going to look at. It says out of survey respondents, 40% indicated that they would like to travel. So that's going to be what we'll call the probability of the good result. We'll just say the probability of the good result is 40% would like to travel. which we could just say is 0.4 or 0.40. However you want to look at it. That's what we're looking at here. I'll leave it as 0.40. Okay, and so if that's the probability of the good result, probability of bad result would be 1 minus 40%, or it's going to be 60%, which is equal to 1 minus 0.40, which is going to equal 0.60 or 60%. Okay, so that's the probability of Q, or the probability of failure, if you will. So it says that's the probability of traveling to one foreign country within the next 5 years. If 30 respondents, so that's our n equals 30, are randomly selected, find the probability that more than half want to travel to a foreign country in the next 5 years. So here we go. We want to know the probability that more than half. So more than half would be 15. So probability that x is greater than 15. So more than half does not mean equal to. It'll make a difference here. It's just greater than 15. Or I could have said 30 divided by 2 if you wanted right there. That's what I'm trying to find. That's the probability. Okay, so to use the normal approximation, first we need to check two things. We need to check first, if I take n times p, what will that equal? 30 times 0.4 will equal 12, I believe. I'm going to check that real quick. And it needs to be greater than 5. So I'm just going to type this in, 30 times 0.4. And you can see that's 12. Now, we're going to be in good shape when we do n times q, because q is larger than p as it was. So whenever I multiply this, this will definitely be greater than 5. So I should put that's greater than 5. Here, 12 is greater than 5, so that's good. And then here, times 0.6, this would be 18. And this also is greater than 5. So we're good. On both cases, we're good. So we can use a normal approximation. So what would be the mean? If you want to know the mean is going to equal n times p. It's the number of samples times the probability. N times p, which we already have, is 12. That is our probability, or excuse me, our mean right there. So that was n times p. Now let's talk about how you find the standard deviation. The standard deviation is found by taking the square root of n times p times q, which means this would be the square root of 30 times 0.4 times 0.6. Let me make that, let me do this in parentheses, it'll look better. Square root of 30 times 0.4 times 0.6. There we go. So we're going to type all that. I'm going to use a calculator now. I'm getting a little bit past where I want to use mental math. Square root of 30 times 0.4 times 0.6. And we get 2.68, which is approximately 2.68. Now, if we are going to use the central limit theorem, we need to find the standard error. So remember, the standard error is calculated by taking this standard deviation, which is 2.68, and dividing it by the square root of the samples, which here we had 30 samples. And you know what? I should be using some of this. So the mean of the population here, we said was 12. And this value, we said was the square root. Let me just copy this right here. I'll let the calculator keep it perfect. There's the standard deviation of the population. We have 30 here. We'll get to the mean of the sample in a second. But you can see here that this value, 2.68 divided by the square root of 30, 2.68 divided by the square root of 30 is the same number you have listed right there. So those are the same values. So the calculator is solving for us. And it says the standard error here is 0.4898. Let's just say 0.4899. Let's say 99 like that. Or I could just say 4.9. Let's just do it that way. 0.49. And then after we found the standard error, what we've been doing is finding the z-value after that. So z would equal, we want to know the probability that's greater than 15. That's going to be our sample mean, if you will, minus the mean of the population, which is 12, divided by the standard error, 0.49. And I should have done a squiggly right there, because ultimately that number was rounded. And so let's see what we get here. My z-value, m of the sample right there. The mean of the sample we're saying on this problem was 15. So I put that in, and we should get 6.12 if I've done this right. Let's check here. Our calculations, we're going to say 15 minus 12 divided by 0.49, it is 6.12, roughly 6.12. Now that we know that, we want to know what's the probability. It's going to be a very limited probability here. We're finding the probability that it's greater than 6.12. 6.12. That is an extremely small number, which is basically 0. And that might be our hint that something's wrong here. Why is it basically 0? Well, there's two reasons. One is when we're using a normal approximation of a binomial, what we're not going to do is end up using this standard error. So this part is going to go away, and what we'll leave instead for the denominator is we will just leave the normal sigma. So what I'm going to do here is delete this, so we can say, okay, that's not our value that we're looking at, because that 0 was not even reasonable. So what am I going to change now? Let me see if I can delete it where I want to. Perfect. Let me get that out of there. What I'm now going to say is when we find our z-value for a normal approximation of a binomial, we'll just leave the normal sigma down here, which we had as 2.68. 2.68. And this is what we're going to solve for. And not only that, you may remember that I said on our probability, there's a correction factor. And so at this stage, I'm going to show you that. So where is that correction factor? Here it is. That when you're doing binomial, you don't even find the probability as given normally. So we want to know when the probability was greater than 15. What this says to do is you actually are going to have to solve this as the probability being greater than 15 plus 0.5. So with the correction factor, this probability is actually going to become the probability that x is greater than or equal to 15.5. This is the correction factor. And so I'm going to work this through again, and this time I will show you the calculator that's designed for it. So if you're doing binomial, slide on down a little bit. I'm going to just turn this one off for a moment. Slide on down, and now let's put in our value. So how many samples did we have here? We had, if I remember right, 30 samples. The probability was 40% or 0.4 of traveling to a country in the next 5 years, one foreign country. That meant the probability of failure was 60%, which that calculates for us. And so this creates a binomial, or it takes the binomial distribution and it normalizes it. It gives you here looking at it as a normal distribution. We want to know, given this z value, what's the probability that more than half, that means more than this 15, want to travel. So now you can see this is going to be more than 0%. And so over here, if we want to know what's the probability that more than 15 travel, you can see the percentage there. It's going to be 13%. Now, if I wanted to get the z value, if you're wondering, what does that z value do for me? Let me put this on there. This probability, the probability, this is going to be your answer here, just so you're not confused. 15.5 is going to be approximately 13.2%, or 13 point, I've been doing 2 decimals, let's say 18%. We'll travel to at least one foreign country over the next 5 years. The probability that over half the people travel, even though the overall probability is 40%, what's the probability that out of 30, over half will actually do it? It's 13.18%. Okay, so what does this number have to do with anything? Well, this would be if you were using the normal or the central limit theorem here. I would come back here and place this number of 2.68. That was the thing I told you we needed to change. And then I would, let me turn this one on, go to this graph. We would look at this being our z-value, 1.119. And when I do that, you'll see that this value happens to be the same as what we had over here. 13 point, this is 16, this is 0.18%. Either way, those are very, very similar numbers. And it probably has more to do with me just not typing it and rounding that a little bit closer. So the more, we can get more accurate by typing in more values. So that's how you could solve that there. Let me go ahead and write in this z here of 1.119. And so that's if you were going to use the normal distribution from 0 to 1, your z value that you would use is 1.119. If you want to use my calculator, you could just stick with the numbers like that. All right, so I'm going to let you try one. Simply put, if you want to use the calculator, you can. You just need to use the normal approximation of a binomial distribution. That should say distribution here. And you could use this to come up with your normal distribution. Pause the video if you need more time. All right, example 5. Trail ride. Hosts of a ranch estimate that percentages of guests who are interested in trail rides to be 70%. So that's given us the p value, that's the probability of success, we'll say, is 70%, which we could list as 0.7 or 0.70. Now, our probability of failure then would be 1 minus the 70%, which would be 30% or 0.3. It says, in order to have a trail ride, there must be at least 10, but no more than 15 riders. If there are 17 guests at the ranch, what is the probability that there will be one trail ride? Okay, so we need to come up with, out of these numbers, which one is our sample and so on. How many guests are there? The answer is there's 17 guests. So here's our deal. We have 17 guests, but we want the probability that the random amount of samples to be between 10 and 15. So let me write out the probability this way. We want to know the probability of having between 15. Oh, I'm sorry, between 10, but no more than 15. Having at least 10, that means you can be equal to it. But no more than 15, which means you could have 15. So I need to put 15 equal there. So this is the probability that I'm looking for. And so this time, instead of getting to the end and saying, okay, now there's correction factors, let's go ahead and check out the correction factors. So if you are equal to a number, notice what you do. Let me start here because I wrote it, or let me start. We first said we are greater than or equal to 10. Which means you need to take that 10 and subtract 0.5. So the first value would be the probability of 10 minus, I should have wrote it out completely the first time around, is less than or equal to x. And now we're going to say less than 15. And so let me go find that probability. What's the probability of being less than or equal to 15 is I would add a 0.5. So I need to add a 0.5 here. 15.5. So my actual probability, this is the correction factors. When I solve this, we're going to be looking for the probability that the random variable here, this x, is, that's supposed to be a 5, 9.5, sorry. That 9.5 is less than or equal to x, which is less than or equal to 15.5. And I realized there, let me correct this, I'm sorry. I meant to put the correction factor, which is plus 0.5. Okay, so there's my correction factors. That's the probability I'm looking for. So let's look at this over here. I'm gonna change these values. Let me just turn this one off because that's not the values I want anymore. We're gonna say that there are 17 guests. the probability of them wanting to ride is 70%, which means it's 0.3% or 30%, not 0.3%, I'm sorry, 0.3 of the total, or 30% will not want to ride. And so now when I look at this normalized distribution of the binomials, I want to know what's the probability that there are a minimum of 10, a maximum of 15. If I put in those numbers, I get the wrong answer. That's not the right answer. 79% is not right. Why is it not right? Because I need to use the correction factors. I need to actually say from 9.5 to 15.5. The actual probability here is going to be approximately 0.869 or 86.96%. So almost 87% chance that they'll have one trail ride. Now you might be saying to yourself, oh, Mr. Voorhees, this time you didn't do all that other math. Well, you don't have to using the calculator, but if you wanted to, remember the values you first do is you need to check if n times p, which in this case was 17 times, use this to 0.7 is greater than 5. So when I check this out, let's see here. 17 times 0.7 is 11.9, so that was good, which that's greater than 5. And you would also check n times q, which this one's going to be a smaller number. Let's see what 17 times 0.3 is. Oh, 5.1, barely made it. So this is, if you were going to be using a standard normal, you'd need to go through this process first. Now we would say, all right, this happens to be the mean. The mean here is going to equal n times the probability. This number of samples times the probability, which we had is 11.9. And the standard deviation, we would do the square root of the n times p times q, which in this case, let me just write it out, n times p times q, which would equal the square root. We had 17 times 0.7 times, oops, forgot the parenthesis, 0.3. And let's see what this value is. This is our standard deviation. So if I want to know the square root of 17 times 0.3 times 0.7, the order doesn't matter when you multiply, unitive property there. We get 1.889. That's our standard deviation. 1.889. Whoops, 889. There we go. And now if you wanted to find your z value, the z would equal, the mean we would be checking for, you would need to use these two x values. So we'd have two z values. Z1 would be 9.5 minus 11.9 divided by that 1.889. That would be your first z value. Your second z value that you would have to find for this particular problem, you would take a 15.5 minus the 11.9 and divide that by the 1.889. And if you did those two things, you would be able to use just a standard normal when solving this. So let me say here, 9.5 minus 11.9 over 1.889. This is a z value of negative 1.27. Some people call this a z score. Negative 1.27. And over here, let's see what this z-score value would be. If I change this to a 15.5, I get 1.91, 1.91. And so if I use the standard normal from, let me just type these in here, negative 1.27 to 1.91, you can see we get the same number here, basically the same number. So I should have just come up here and done the standard normal. So again, these z values would be if you were using a standard normal distribution. That's what a standard normal distribution, that's how you would represent a normal distribution with the mean of 0 and a standard deviation of 1. These would be the z values you'd use to find that probability. Okay, so I gave that to you a lot quicker using the calculator. And then over here, as you can tell, it can kind of get confusing at times going through all the numbers. Here's one for you to try. I'd recommend just using the calculator, but do whatever is best for you. Example 5, pause the video if you need to.